The flight envelope is the safe box an airplane is designed to fly inside, and stall margin is one of the most important distances inside that box. When pilots, engineers, or instructors talk about an envelope, they are talking about boundaries. Not a paper envelope, but an operating envelope. The range of speed, altitude, load factor, bank angle, configuration, angle of attack, and energy where the airplane can be controlled without exceeding aerodynamic or structural limits. The word can sound abstract. In the cockpit, it becomes very concrete. Inside the envelope, the airplane has margin. Near the edge, the airplane starts asking for respect. Outside the envelope, the pilot may have fewer options, less control authority, or no approved margin left. This video focuses on one part of that picture, the stall margin and the angle of attack envelope. It is educational orientation only. It is not aircraft operating guidance, and it is not a checklist. The goal is to build the mental model. Start with angle of attack. NASA defines angle of attack as the angle between the wing's chord line and the flight direction. That angle has a major effect on lift. Increase angle of attack, and lift usually increases up to a point. Past that point, the airflow can no longer stay smoothly attached to the wing. The wing exceeds critical angle of attack. Lift drops, drag rises, and the wing is stalled. That means a stall is not really a speed event. It is an angle event. The FAA Airplane Flying Handbook emphasizes that a stall is caused by exceeding critical angle of attack, and it can happen at any airspeed, any attitude, any power setting. Airspeed is still useful, but it is not the root cause. Angle of attack is the root boundary. So what is stall margin? Stall margin is the distance between where the airplane is now and where the wing reaches critical angle of attack. Imagine a gauge with 3 regions. Green is normal angle of attack. Yellow is high angle of attack, where the airplane is closer to stall. Red is critical angle of attack. The margin is the space between the current needle and the red line. A key point: stall margin can shrink even when airspeed does not look frightening. In a level, unaccelerated condition, the airplane may need a certain angle of attack to produce lift equal to weight. But if the pilot pulls harder, banks steeply, encounters turbulence, changes configuration, or tries to maintain altitude in a tight turn, the wing must produce more lift. More lift demand usually means more angle of attack. More angle of attack means less stall margin. That is why bank angle and load factor matter. In a level turn, the wing has to support more than simple weight because lift is tilted. The FAA explains that as load factor increases, stalling speed increases. A classic example is a 45-degree bank turn and a 60-degree bank turn. The more load factor you ask the wing to carry, the closer the stall boundary moves in speed terms. The critical angle of attack has not changed in a simple way, but the speed at which the airplane reaches it has changed. This is one reason the flight envelope is not a single line. It is a shape. At low speed, the left side of the envelope is stall limited. At high speed, the right side may be limited by structural speed limits, Mach effects, flutter margins, or control forces. At high load factor, the top of the envelope is structural or aerodynamic. At low or negative load factor, there are other limits. The airplane is not just asking, am I fast enough? It is asking, how much lift am I demanding in this configuration, at this speed, altitude, and angle of attack? The common Venn diagram shows this beautifully. The horizontal axis is airspeed. The vertical axis is load factor, or G. On the left side, stall speed rises as load factor rises. The stall boundary curves upward. On the right side, structural limits and never exceed speeds bound the airplane. The safe operating region sits inside the lines. That is an envelope. But the Venn diagram is not the whole story. For modern airplanes, the real envelope is multidimensional. It includes Mach number, altitude, flap and slat configuration, landing gear, icing, center of gravity, thrust, bank angle, and flight control laws. NASA research into envelope protection describes estimating boundaries such as maximum angle of attack and maximum bank angle under current conditions. That is the deeper idea. The safe boundary is not one fixed number. It depends on the airplane's current state. Now connect that to stall warning. Transport category rules require a clear stall warning with enough margin to prevent inadvertent stalling. The warning is not supposed to happen after the wing is already fully stalled. It belongs before the boundary, where where the pilot can still reduce angle of attack and recover margin. That is why systems like stick shakers, stall horns, low-speed cues, and angle of attack indications are really envelope awareness tools. They tell the crew that the airplane is moving toward the edge. Angle of attack envelope is a useful phrase because it shifts attention from one airspeed number to a real aerodynamic limit. AOA is the direct relationship between the wing and the oncoming air. If the airplane is slow and level, AOA may be high. If the airplane is fast but pulling hard, AOA may also be high. If the airplane is climbing steeply, turning, or recovering from an upset, the nose attitude on the horizon may not tell the whole story. The wing cares about relative wind. Configuration changes move the picture too. Flaps and slats generally change the wing's lift characteristics and stall behavior. They can allow higher lift at lower speeds, but they also come with speed limits and procedure limits. Clean configuration, takeoff configuration, and landing configuration each have their own expected margins. This is why approved speed schedules and configuration procedures matter. They are practical tools for staying inside the envelope. Altitude matters as well. At high altitude, the margin between low-speed stall and high-speed Mach effects can narrow. Pilots often call this a narrower high-altitude envelope. The airplane may have less excess thrust, thinner air, and less room between buffet boundaries. Again, the point is not just one number. The point is margin. Stall margin also connects to energy management. Airspeed is kinetic energy. Altitude is potential energy. Thrust can add energy, but it may take time. Drag removes energy. A high angle of attack creates more induced drag, which can pull speed down unless power and pitch are managed correctly. If the pilot keeps asking the wing for more lift while energy is decreasing, the airplane can move rapidly toward the stall boundary. This is why the phrase "reduce angle of attack" is so central. If the airplane reaches a stall warning, the first aerodynamic problem is that the wing is too close to critical angle of attack. Power can help rebuild energy, but power alone does not change the fact that the wing must be unloaded. The airplane has to be moved back inside the angle of attack envelope. There is a subtle trap here. Pilots often memorize stall speed, but stall speed is conditional. It changes with weight, bank angle, load factor, configuration, and sometimes contamination. The published stall speed is a useful reference, not a magic shield. AOA margin is a better mental model because it explains why the same airplane can be safe at one speed in one condition and close to the edge at another speed in another condition. Icing or contamination can make the envelope smaller. Ice changes the shape of the wing, disturbs airflow, and can reduce the angle where the wing stalls. The pilot may think they have normal margin, while the wing behaves differently. That is why contamination is treated conservatively. It is not just extra drag. It can move the aerodynamic boundary. Automation can help protect the envelope, but it can also hide the trend if the crew stops monitoring. Envelope protection systems, flight directors, autopilots, low-speed cues, and stall warning systems are valuable. But the crew still needs to understand the shape of the problem. If the airplane is slow, high drag, high bank, high pitch, or asking for more lift than the wing can provide, the envelope is shrinking. The practical mental model is simple. Picture the airplane inside a three-dimensional room. One wall is low-speed stall margin. Another wall is high-speed or Mach limit. The ceiling is structural load factor. The floor is negative load or minimum controllable margin. Configuration and altitude can make the room bigger or smaller. Angle of attack is the wall that matters most. The pilot's job is not to scrape the wall. The pilot's job is to keep room. So when someone says work envelope or flight envelope, hear this: the safe operating range. When they say stall margin, hear this: how much room remains before critical angle of attack. When they say angle of attack envelope, hear this: the usable range of wing angle before airflow separation and loss of lift. The final lesson is that envelope awareness is not just for test pilots or engineers. It is a cockpit survival skill. Airspeed, attitude, bank, load factor, configuration, altitude, and automation mode all tell part of the same story. The wing is always negotiating with the air. The stall margin is the distance left in that negotiation. Respect the margin and the airplane stays inside the box.